Good morning, everyone. So today we are going to give a presentation, and the title is called Using Deep Learning to Extract Information from Remote Sensing Imagery. So before we get started, so I want to know, so how many people here have experience with Python? Okay, almost everyone. So how many people have experience with deep learning? Okay, I will give a self-introduction to both of us. So my name is Han. So I work as a software engineer in the raster and the imagery team at Esri. And my colleague, she's Dan, and she's a product engineer, and we are working in the same team. So then we'll give the first introduction of our presentation today. And so, yeah, I will hand over my microphone to Dan, and she will start.
Good morning, everyone. Thank you for being here. Today, we are going to talk about how to use deep learning models with ArcGIS to extract information from imagery. So here's the overview of our presentation today. First, I'm going to talk about how ArcGIS and deep learning are integrated to extract information from imagery. Then I will talk about the current deep learning tools in ArcGIS. I will demonstrate how to create training samples using our tool. Then Han will talk about the deep learning package. It's a concept that we have in ArcGIS. And he will demonstrate how to write Python raster functions for deep learning inference. And he will briefly talk about the Esri model definition file for this deep learning package. The third part, I will talk about deep learning inference tools in ArcGIS. I will demonstrate how to perform deep learning inference with our current tools. We will provide some resource about deep learning in ArcGIS. So maybe at that point, you can take a picture of the resource link. And finally, we will have Q&A session. So we appreciate if you can save your questions in the end so that we can have this presentation go on schedule. What is deep learning? Probably most of you have heard about deep learning. There's a hard code definition about deep learning. It refers to algorithms that break down complex problems using layered algorithm architecture known as neural networks. It can leverage a large quantity of training data and computation power. Deep learning is a subtype of machine learning. So in other field of machine learning, we still need human beings to input features, to extract features, and for the machine to learn. But for deep learning, since we input a large quantity of data and we use complex convolutional neural network to train the model, we don't need to do that step. The computer will learn the feature extraction and classification. There are a lot of deep learning use cases in computer vision field. So on the top, it is the classic application use cases in computer vision. Each column represents one kind of task. For example, image classification, object detection, segmentation, semantic segmentation, and instance segmentation. So as you can see, we have a lot of imagery data in GIS, satellite imageries, and drone images. So on the second row, on the bottom row, as you can see, we can apply those different tasks in GIS field as well. We can use image classification to classify the geotagged photos. For example, here we have these geotagged photos to be classified as dense crowd. And we can use object detection to find objects in our satellite images or drone images and map them. we can use semantic segmentation in land cover classification. And we can use instance segmentation to detect more precise boundary for building footprints. A typical deep learning workflow, or I should say every deep learning workflow, is composed of 3 tasks. First is to create training samples. A deep learning model needs a lot of data, a large quantity of training data. So we need to prepare the training samples for the model. And then I think the most important part is to train the model. So data scientists will use different structures and to feed the data into their model to train a good model. After a model is well trained and you are satisfied with the accuracy, we can put the model into production mode. We perform inference with newer images. Here, this diagram shows how ArcGIS Enterprise and ArcGIS Pro is integrated with deep learning. We have 3 types of roles: ArcGIS professionals, data scientists, and ArcGIS users. There we have different roles. It doesn't mean they have to be different persons. You can, as a single person, can do all these tasks. So first step is ArcGIS professionals to communicate with data scientists about their needs, about what metadata format they want, and what kind of image chip format they want. So they have a lot of existing GIS data, or they can create new GIS data to use in their training sample preparation. They use our tool called Export Training Data for Deep Learning in ArcGIS Pro or on the server to prepare samples. After that, they will hand over the training data to data scientists to develop their model. So here, data scientists can train their model in their independent environment, or they can leverage the ArcGIS API for Python and host it Jupyter Notebook in ArcGIS to train the model. So when the model is well trained, and the data scientists can now deliver the deep learning model package back to ArcGIS professionals. The deep learning model package is composed of Esri model definition file and the model file. Usually it's a binary file, and optionally a Python raster function for inference. After receiving this model package, ArcGIS professionals will examine whether it works, and then he or she can deploy this deep learning model package either on their local desktop in Pro or share it to their portal in their ArcGIS Enterprise. With that shared items, more users can use this model to run inference with our detect objects using deep learning tool or classify pixels using deep learning tool. And even the results, if they look good, they can publish and share those feature classes as feature service or classified images as image service so that more users can use the result. We have several tools in ArcGIS to do deep learning work. Create training samples. In ArcGIS Pro, we have Training Sample Manager for you to create new GIS data and use that in Export Training Data tool to prepare the training samples. In ArcGIS Image Analyst Toolbox, we have the inference tools, detect objects using deep learning, and classify pixels using deep learning. We also have a post-processing tool, which is called non-maximum suppression. So this tool is to post-process objects detected from your imageries. So the model will not be perfect. There would be some duplicates of the features in your feature class. So this tool is to help you remove those duplicate features based on some threshold. We have also these tools supported in ArcGIS enterprise ArcGIS server in raster analytics. So as you can see here, we have a bunch of tools, which is actually the geoprocessing services for you to manage deep learning model package on your portal, and also run perform inferences with raster analytics. You can leverage the distributed raster analysis. For those tools on raster analytics server, there are different clients who can consume them. We can use ArcGIS REST API to run this inference and prepare training sample. And in ArcGIS API for Python, we have this ArcGIS Learn module to run inferences and prepare the samples. In ArcGIS Pro, when you connect to your portal, you can also run these raster analytics tools. From Portal Map Viewer, you don't even need to install software. You can run those tools from an internet browser. So first, I like to demo how to use export training data for deep learning with ArcGIS Python API. So here's a Jupyter Notebook. I'm using ArcGIS API for Python to call my RA tools to prepare. Oh, really? Okay. Display settings, yeah. Okay, good. Okay, good. Here's. Oh, do you see clearly? Yep. Okay, good. So here's this Jupyter Notebook for me to use ArcGIS API for Python to export training samples. First, I'm going to import those necessary modules. And now I'm connecting to my portal with Raster Analytics Server federated. And now it's going to create a JS object. I have pre-published some images on my portal. So this is a fully labeled land cover data. It's going to be used as the label data. And I have another images with RGB band. So it will be used as the input in the training sample data. Here with this get underscore data stores, I'm trying to get the data store that is configured on my RA server. I'm going to input my image chips into this folder. Here, I'm just enable the verbose geoprocessing images. Here, this is the function in ArcGIS Learn module to export training data. Let me run this first. So this function takes arguments. The input underscore raster is an imagery layer object, and the output location is what I just gave. And this input class data also takes an imagery object or a feature layer object if you are preparing data for detecting objects. So here you can specify the chip format. It can be TIFF, PNG, JPEG, and MRF. And here we define the tile size for the training samples and the stride size. The stride size is essentially defining how the image chips are overlapped or distant. And we support different metadata format. So these classified tiles is especially for semantic segmentation. Then the results will be a pair of image chips. And the class value field, if in your land classification data, we need a field for telling the function that which is a class value. So here I put it at long because I use the field class value. So here in the context argument, we have this start index and export all tiles. So export all tiles is true because I know that my label data is fully labeled. That means every pixel in the imagery is having a label. If you prepare data for detect objects, you may not have features everywhere, so you may want to set this as false. It looks like my job is finished. So I can use this list underscore data store underscore content to list all these image chips in my image folder. As you can see, there are about 560 image chips. Similarly, there will be another folder called labels. So in this folder, we have labeled, that means the image chip from the land cover classification imageries. So if we look closely in ArcGIS Pro, as we can see, there are two folders. One is image folder, another is label folder, and from the label folder, we have this image chip with the land class values. And from the image folder, we have the image chips from the RGB band imagery. So that's how we use export training data to prepare training samples. Next, I will hand over to Han.
Okay, so once the data scientist gets all the training samples, he will train a deep learning model. So in this case, it's a semantic segmentation model. So it can classify every pixel in the input raster to a certain land type class. So and then the data scientist needs to bring the deep learning model back into the ArcGIS platform. So he will prepare a deep learning model package. A deep learning model package is composed of your Python raster function, an Esri model definition file, and probably your model files, binary files. And the most important component of the deep learning package is your Python raster function. And that defines how you can inference the model in Python. So I will first start with the Python raster function introduction. So Python raster function is ArcGIS Python interface for you to write your own raster or imagery workflow purely in Python. So the module is loaded and executed by a Python adapt function. And the Python adapt function is Python aware. It understands your Python code and executes your code. So we will first take a concrete view of how a simple hello world Python raster function looks like. So this is a simple hello world Python raster function. And it first in the init method, it gives just the name of this Python raster function. It's called a hello world function. And in the second method is called get parameter info. So this defines all the input of this Python raster function. And in this case, it only has one input, one parameter. and the data type is raster. And the workhorse in this function is update pixels. In the update pixels, and there are 3 lines of code. So the first line is you get your input raster. Because your input raster name is R, so you can get your input raster just called by index the dictionary R underscore pixels, and you add that pixel, and that's a numpy array actually. So you add that numpy array by 10, and then you return the pixel block to Python adapt function. And then ArcGIS, if you execute this Python raster function in ArcGIS, you get a result raster that has every pixel added by 10 from the input raster. So any question at this point?
In the parameter, what mean double star pixel blocks? What's the data type parameter? Double 2 star.
Which line do you point to?
Line 13.
Oh, so it's so that's a dynamic like double star. That's a dynamic means is a dynamic parameter. So it can be there can be a lot of like in Python it can be a variable length of parameters. So you can have a lot of information, like you can get your mask, you can get your pixel block mask. You can call pixel blocks square R mask, and you can get your pixel values. So in Python, that's a variable length of variable. That means, so yeah, and you can index the parameter by the name. So in this case, I only get the pixel value, so I got R pixels, not the mask. I added by 10. So if I execute this Python raster function, I get my input raster added by 10. So besides the 3 APIs I have here, so there is actually a lot of APIs you can implement. So some common APIs is listed here. Get parameter info, you define your parameters, and get configuration, you declare how your input raster should be read. And if you want your Python raster function output a raster, you need to implement the update raster info, and that actually defines what your output pixel raster pixel type or like number of bands, those kind of properties. And if you want to output your raster, inference your raster to get a feature class, you will need to implement get fields and get geometry type. So that defines those fields, output fields of the output table, and the geometry type defines whether the output feature is a point or polygon or polyline, those kind of things. So the most two important APIs are update pixels I just show in the Hello World example. And if you want your raster to save a feature class, you will then need to implement the vectorize. So now I will give a pure Python demo. So in this folder, I have a deep learning model, and its last file is from TensorFlow. I tried that using TensorFlow. I ended up with a frozen PB file. That's the model file. And that model file has all the weights and model architecture saved in that file. So you can think a model file as a function. So once you have trained a model, you can think of a model file as a function, and you can inject some data, and you get it X, and you get your output Y. So the first step is a pure Python. So in this Jupyter notebook, I first import all the necessary libraries, and then I have a test data. I open the data and I show the data. So this is RGB image chip. It's exactly the image chip I get from Dan. So it's 513 by 513 in both dimensions. Because the model I trained use a batch, so I expand the numpy array to have a batch dimension in the front. Now I write a function to load the PB file into a graph, into a TensorFlow graph. And TensorFlow graph is a function I just made. Now I load that PB file into a TensorFlow graph and this object. So now I'm going to start a TensorFlow session. A TensorFlow session is a working environment. You can just do some operations within the deep learning framework. So, and this is a function evaluation. I put the array, and the array is an image object I just opened. I put the image array and I feed that array into the TensorFlow graph. I get my output. And then I can see the output is exactly the same size as my input. And it's only one band, and it's an integer type because we are classifying an input image chip to a land type. So each land type is integrated by an integer number. So I show the one band integer output using a color map. And here is what the model tells us. So I got the image opened on the left, and I got the output segmented result on the right. So you can see the result for one image chip. So once I have this work in the Python, so how can I bring this back into ArcGIS? So we use that Python raster function. So in this Python raster function, I have that code working in my Python. So I want to execute that code in every raster in the ArcGIS. So this is a Python raster function. So first is everyone does the same thing in Python. So first import all your packages. And then I copy the load from the graph I have in the Jupyter notebook. So this takes a model path, that's a PB file, that's your binary TensorFlow file. And you import that model into your TensorFlow graph object. Now I have the class demo. And this is a Python raster function declaration. So in the initialization call, I declare the model where the model is located, and then I save it into graph. And the get parameter info, that if you want to use deep learning workflow, that parameter info, the first three has to be fixed. The first parameter is your input raster, where you want your deep learning model to work on. And the second is a model, and that's actually the Esri model definition file. And the third is your device, because our GB2 has a device setting in the GPU environment. So, and you can give a device index, whether you want this GB2 to be executed in the GPU or CPU. So you will receive that device ID in your Python raster function. So that's the parameters of this deep learning Python raster function. That has those first three parameters have to be fixed. Now the get configuration, we know that the get configuration is where you define how your input raster should be read, because we know our model works on the RGB band. So I need to tell the ArcGIS that, okay, give me the first three bands, and that's called the extract bands. And I want to work on tile size of 513 by 513. So I declared my tile size width is 513 and my tile size height is 513. And I don't want the tile to be overlapping, overlapped with each other. So I say padding is 0. So once I have this configuration, if I work on the GB2, if I open the GB2, I want the GB2 to be work on a very large raster. I usually, every pixel block I receive in the update pixels is exactly 513 by 513. So I can inference every small image chip in the update pixel call. Now the update raster info, because this is a NAND classification, so I know my output band count is exactly 1, and my output pixel type is 4 bytes integer. Now in the update pixels, and that's a workhorse, and the same thing happens as a hello world example. So I get my input imagery, and then because ArcGIS Python adapt function gives you number of bands, height and width in the order of number of bands, height and width. So I first need to transpose to the order of height first, and width second, and number of bands third. And then I do the same thing, like I expand into a batch, as in the Jupyter Notebook. And I also open the TensorFlow session with the graph I just loaded in the initialization. And I feed the data with the batch. And I can also get the same prediction, classification prediction. And then I return the pix block to the ArcGIS Python adapt function. The ArcGIS adapt function will save that into the raster, output raster. And these updated pixels will be called like iteratively in a loop. So each time the Python adapt function gives you a pix block exactly exactly the size you declared in the get configuration. So now I have finished my Python raster function. So I need to have an Esri model definition file in order to make the GB tool work. So a simple like Esri model definition file, you only have one property. It's called the inference function, and that's mandatory. So inference function points to the Python raster function you just you just finished. So it points to the inference function, and then because I hard coded my binary file, my TensorFlow binary file in the Python script, so I don't point. And right now, this code is this property is not used. So only the EMD file and the PR file is sufficient now. So now I can bring the EMD file to ArcGIS Pro. So this is called the classified pixels. I have the EMD as a third parameter, and the EMD points to the Python raster function. And then the ArcGIS know how you can bring your model and make it work in the ArcGIS Pro. So I bring the EMD to the third argument, and I have my input raster, and that's what we just saw in the Jupyter Notebook. And I also opened it here in the ArcGIS Pro. So I save it to the to this TIFF file, and then I can run the GB tool. And while it's running, because it takes 1 minute, so I can explain. So what you can do, like to further improve your Python Esri model, deep learning model package. So right now, I think we just hard coded. We hard coded the PB file here, but usually that's not a good coding practice. So usually you will give your EMD to someone who doesn't understand any Python. So probably you can give him an EMD file. He can then understand so what's inside the deep learning package. And a JSON file is more understandable. So you put your model file location, and maybe he can change that later without touching your Python. So you give your model file location in your Esri model definition JSON file, and then you can dynamically retrieve the package from the EMD file because in the initialization, the Esri model definition file is also given to you by embedded in these KW arguments. So let's see if, okay. So the tool also finished. So let's see the segmented result. So I will change the symbology to discrete values. Then you can see, oops. Unique values. So I need an attribute table. So that's how the GB tool, so that's how you can make your deep learning model working in the ArcGIS Pro platform by implementing your own Python raster function. And yeah, this is successfully run. So, okay. So if you have some models that needs your own Python raster function module, and we also provide some built-in Python raster functions for well-known training implementation. So in these cases, you don't need to start from scratch by writing your own Python Rust function. Like for example, if you use the TensorFlow object detection API, we have built-in Python Rust function to node your model and inference that. So you don't need to start from scratch. And we will later in the last slide, we will provide some resources and you can find where those built-in Python Rust functions locate. Okay. Then we'll summarize the RA server functionalities in the new release, and I will give that to them. Before that starts, I wonder, is there any question? Okay.
How we can see the accuracy your classification?
Oh, okay. In this model probably has like 70 to 80 pixels accuracy. So that means if I use this model I use that model in my validation data set, I got maybe 70 to 80 pixels classified correctly. But it's all dependent, it's all up to your data scientist or your training, whether your training performance. So I just use this model as an example, but you will bring your own model, and if your model works fine, it's fine. And so if your model doesn't work perfectly, you will improve your training to get a perfect model.
Is there any way we can use deep learning further classification? I mean, more deep learning into high level and achieve higher accuracy. So learning more. I mean.
Oh, so this part is about the inference. It means so we assume you already have the model. So actually the performance is fixed by this point at this point. So in the training stage, you probably can do a lot more, but that will not be covered by this session. That's a training stage.
Thank you.
Okay.
Can you switch? Thank you, Han. So I have received this deep learning model package from Han. As you can see, I have only actually two files. One is an EMD file, another is a binary model file. So let's look at what's inside the EMD file. The EMD file is basically a JSON file. It describes the parameters about my model. For example, it is using TensorFlow as the model framework, and it is used Deep Lab API for my deep learning model. So here I specify my model file name. Since it is located in the same folder as my EMD file, so I don't have to specify the absolute path. And the model type is image classification. I have also other information, the band of the input raster and the tile size, width and height. Here it defines the classes that my model can classify. From there are 6 classes in here, and also it defines the name and the color, the color ramp. Why don't I have the Python raster function? Because we are using the built-in Python raster functions. For example, in my Pro installation place, we have these built-in Python raster functions for deep learning framework. We have CNTK, Keras, and TensorFlow. As you can see, in TensorFlow, we have Deep Lab and Object Detection API. So my model, this particular model is actually using these deeplab.py and imageclassify.py to do the inference. So let's go back to my Python Jupyter notebook. And here in this demo, I'm going to still use ArcGIS API for Python to manage my deep learning package. So first, I'm going to import the necessary modules and connect to my portal. Similarly, I'm creating this .js object. And here it is just describing what the EMD files is. So we have seen that. My model package is located on my local desktop. So I'm specifying the path. Oh, by the way, here, this is a model package because I have zipped the EMD file and the PB file and changed the extension to .dlpk. So that's an item type that can be recognized by your portal. Then I'm creating this ArcGIS.js content manager object. And there's a method called add to upload your item. As you can see here, I'm specifying the type of the item. It's deep learning package. And type keywords, title of my item, and some tags for the item to be better searched. Since I have already uploaded one item, so I'm overwriting it. And now it finds the land classification model package on my portal. Next step is to install the model. So there's this learn module, and it has the model class. We can create the model object and use this install method to install the model. So what the installation does is to unpack the model package and then copy that to your server location. So in this case, I installed my RA server to this to my machine. So it is copying this package or the necessary files into this path. Okay, the installation is done. I can also list all the models that have been installed on my RA server. As you can see, I have two models, the land classification model and another model called coconut tree detection. With my model installed, I can now query the information in the model. So I call this query_info method. And it will give me the parameter information of this model. So basically, it's some of the parameter framework model type as we see in the EMD file, and also the model arguments. For example, in this model, I have only one argument that needs to be specified by who's run the model inference. So it's the padding, and the default value is 0. We can change that later. So I have pre-published my my new image into as an image service. So let me search that. And now I have this imagery object. To save time in this demo, I'm going to run this inference for a small area. So now I'm setting this analysis extent, and it is for this sub area. And now I'm setting the analysis extent. Let me run this first. So in this function, under learn module, this classify underscore pixels, it takes the imagery layer object and the model object. And in context, we can specify that whether it will be using GPU or CPU as the processor. So my RA server is configured, is a single machine server. I have one GPU card in one server machine. So I have only one GPU instance there. So I specify this parallel processing factor as 1. If you have a server node, if you have a server cluster, you have like 2 server or 3 server machines on the RA side, you can actually increase this number to take advantage of distributed computing on your RA server. Looks like my job has been finished. And this is the output of that particular image. After you are done with your model, you may want to uninstall the model to save some space in your, on your RA server machine. So now you can call this uninstall method to uninstall that particular model. We still have some time, so I will go through the process of running detect objects using deep learning. So as I mentioned, I have another model on my portal. It's the coconut tree detection model. It is using the same TensorFlow framework. So I can run different models on the same portal or RA server. And still going the similar process. We can query the model information. It's using TensorFlow Object Detection API. And for the model arguments, we have score threshold, padding, batch size. So batch size is this concept in deep learning. When you use batch size, you can speed up your inference. So the default is 1, but you will see later that I'm increasing this batch size. I have pre-published this high-resolution imagery for coconut tree detection. And when we zoom into a smaller area, as you can see, you see these coconut trees. So in ArcGIS.learn module, we have detect objects function. It has similar has similar arguments as the classify pixel function. So input this imagery layer object, model object. And here in these model arguments, so I want to change the batch size from 1 to 16 so that each time my GPU is processing 16 tiles of my image. And similarly, I'm specifying GPU as a processor type. For extent, you can actually set in here in context. So this analysis underscore extent is this extent JSON, it's dictionary, and it is specified as the extent. When we run this model, finally, we will get some results like this. The underline is the input image, and this is the polygons or the bounding box that for each of the coconut tree. As you can see, it captures the coconut tree pretty nicely. So this is how we use ArcGIS Python API for Python to run inference on raster analytics server. Hopefully that gives you a good start. So here's these resources about getting started with deep learning in ArcGIS. This first one is the raster deep learning repo. We have our Python raster functions, those built-in Python raster functions. We all put them here. And we have some examples for each of the deep learning framework we support. So for each of the software release, such as the latest release of ArcGIS Pro 2.3, we have some built-in functions. But through the time, we are also developing new Python raster functions to support more deep learning framework. So this repo will be the latest one. So because the release only captured that single time, but this one is it will be always the latest. And the second repo is the raster function repo. If you want to know more details about Python raster function, you can go to this repo. The third one is the ArcGIS API for Python page. So just last Thursday, we released ArcGIS Python API to 1.6. So in 1.6, it has this learn module. You can use that to call RA tools to run your RA jobs. I believe in Python in Pro 2.3, the API for Python shipped with Pro 2.3 is not updated with this 1.6. So you can actually update your Python API from this web page. It has all kind of links to the repos and the instructions of how to update that. And we also have some story maps and articles about using deep learning in ArcGIS. I suggest you check out if you are interested. And also here is a very good webinar we provided on YouTube. So it's about 1 hour and very informative. You can go check it out if you are interested. So we appreciate if you can take the survey after this session, since we need your feedback to improve our session for next year's presentation. Thank you.